And today we began to discuss weak convergence of probability distributions in infinitely dimensional spaces. This subject arises due to several reasons. One is that, as we mentioned it maybe in the beginning of our lectures, probability distributions in infinitely dimensional spaces arise very naturally when we consider random processes as an element of appropriate functional spaces, random fields, and so on. So we want to have different notions of convergence in distribution in infinitely dimensional spaces. Another reason is that we already have a very nice and powerful tool to investigate weak convergence in a finite dimensional case. Namely, we know that in finite dimensional case, the sequence of probability distributions converge weakly if and only if the characteristic functionals to have weak convergence, to have pointwise convergence of characteristic functionals. But in infinite dimensional case, it occurs that we have additional troubles, and maybe you understand that the problem comes from the fact that in infinite dimensional space we need some additional properties of the function in addition to continuity, non-negative definiteness, and we want to have something else in order to this function to be characteristic function of probability distribution. So we will see what problems will arise and how we can overcome these problems. But our first lecture will be devoted to weak convergence in a very abstract settings. Namely, we will consider complete separate metric space X row is complete separate we will have Borg sigma field. In X row, and we will discuss the weak convergence of probability distribution. N is greater or equal to 1 mu probability distributions on sigma field V. And today we will discuss what does it mean that mu n weakly converge to mu when n tends to infinity. So what is this? I mean, not on the definition, of course, one can imagine very fast definition, but criteria of the weak convergence, properties of a sequence which is weakly convergent, and so on. So let us start. Of course, we will start with the definition. definition. We will say that a sequence mu n weakly converge to probability omega mu, and the n tends infinity to infinity, mu n weakly converges. For all function f, which is continuous and bounded the space x, we have the integral with respect to x of f du n converge integral with respect to x of f du when n tends to infinity. This is the main definition of the subject we should investigate in our lecture. Let us begin with the example. Suppose that our measure mu n is simply a delta measure concentrated at the point un of our space. Then if mu is equal to delta x, delta u, then mu n weakly converge to mu when n tends to infinity, if and only if un converge to u and the n tends to infinity in our space x, the elements of x. So the distance and the distance between these two elements must go to zero. How to check this? In one direction, if delta un weakly converge to delta u when n tends to infinity, then for such function f epsilon, which is equal to 1 minus 1 over epsilon rho uv, and here is plus. We have that the integral from such function must converge to the integral from this function to delta u. Before to write these integrals precisely, let us explain what is written here. Rho is a distance, and symbol plus means the following. if we have some x which belongs to R, then x plus is equal to x if x is non-negative, and 0, 0 if x is less than 0. Okay? So we have such a function, and it is now evident that this function is has the following property: f epsilon from u is equal to 1 for any positive epsilon, and f epsilon v is equal to 0 when if rho v u is greater than epsilon. This function has some form if our space X is good, of course. So the picture is like follows. We have point U, here we have altitude 1, and then we have such a cone which is supplied by the epsilon neighborhood of our point U. And altitude here is equal to 1. Now let us see what is happening with integrals. As we remember, the integral with respect to the delta function is the value of the function, the corresponding point. So what we have the epsilon, f epsilon from un converge to f epsilon from u, which is equal to 1, and n tends to infinity, and this must happen for any epsilon which is greater than 0. So it means that for any epsilon which is greater than 0, there exists such n0. It can depend on epsilon, of course, such that for any n which is greater than n0, epsilon un belongs to this ball B U epsilon. This is exactly the definition of convergence. So in this direction, we prove convergence follows that we have the convergence of the points now let's go back. It is even easy. If you add converge to u when n tends to infinity, then we have the integrals respect to x f du n equal f of un, and it must converge to f of u when n tends to infinity, and this f of u is equal to integral x f mu. So we checked our statement in both directions, and we know that for delta functions, weak convergence mean the convergence of the corresponding points. This example can be generalized probability direction, and one can consider a sequence of random elements in our space. So let us consider the next example. here we have the sequence of random elements xi n and xi random elements on omega f e with values x. And suppose that suppose that psi n converge to psi in probability n tends to infinity. It means, by the way, that for any epsilon which is greater than 0, we have the following probability that rho psi n psi is greater or equal than epsilon tends to 0 when n tends to infinity. This is the general definition. By the way, it will be good to know that now you must have to check that this is a random variable. It happens due to the separability of our space X. So one can consider such probability Qn and require that it goes its probability goes probability for our sequence. Then one can consider distributions of our random elements. We consider nu(n) as an image of initial probability measure under the matrix n. Mu is the matrix I. By the way, it means that mu from subset delta is equal to probability that psi omega belongs to delta. If delta is taken from the Borel sigma field, this is a random event, and one can consider such probability and get such probability measure. So one can organize the distributions of our random elements, and then it occurs that if our random elements converge to infinity, then we have that its distribution converges. So then let us check that this is very easy. So we'll consider any f which is continuous and bounded on our space X. Then one can consider integrals integrals with respect to X. It is equal integral with respect to X. F of u here is p psi n minus 1 u. And now we use change of variables formula from the measures theory, and we obtain the integral on the omega. Yes, here is f of psi n omega psi omega p d omega. The same happens if we use here consider mu. We will get the same integral f from psi omega. Now let us note that the continuous function keep the convergence in probability. So let us mention that this random variables f psi m converge converge psi m tends to. This is also exercise for you. But we have to remember this from the course of probability theory. Continuous function keeps convergence in probability. We proved this in the course of probability for random variables, but here the proof is exactly the same. It is based on the RIS lemma, which says that for any sequence which converge the subsequence which converge almost sure. So one can use this and then get the following conversions. Also, these are bounded random variables. Yeah, let me say that they are bounded by some constant, bounded by absolute value. So one can apply Lebesgue theorem about dominated convergence, and then from Lebesgue theorem one can get that these integrals came to the desired limit. Dominated convergence. One can say that it comes to integral f psi omega p omega, and it is exactly what we want. And tends to infinity, because this is our integral x f omega. So we get maybe expected property that from the convergence probability converges in distribution formulas. In the backward direction, we know already this from probability course that it is really weak. And it does not imply convergence in probability. Now, let me go further with the next example, and we will discuss it by the several reasons. One is the following. We need to understand deeply what is the convergence in absolute space. Another one is that we have not a lot of examples of distributions in abstract space. You can ask yourself, how many examples of distributions I know, for example, in the space C01, or in the space too small. Yeah. So we are now considering the convergence, and also we are solving the problem of enlarging our imagination. We want to have more examples. Of course, one can imagine one can imagine that this example is delta functions can be expanded. Yeah? So we can have a family of discrete measures. On X. What I mean? Let us take capital and in our space X and positive numbers P1, P and capital, which are greater than 0, such that the sum from n small equal to 1 capital n is equal to 1. Then one can organize the following function distribution mu. It is equal to sum from n equal to 1 to n p and delta u n. This is a probability measure which is concentrated in the finite number of the points you have. For any occasion, I will write the action of this measure on the cells. So mu of beta is equal to the sum k equal 1 to capital k. Here is indicator of delta from uk. From this equality, which can be taken as a definition of this measure, one can see that due to these conditions, really the probability measure on our space, and of course it is well defined on the Borel sigma field. Actually, it is well defined even on the all subsets of our space and remains to be measured on this large family of the sets. Large family of examples of measures in our space. Of course, they are not very beautiful, yeah? But still, this family is pretty large, and it is large enough that we can say that the depth with respect to weak convergence in the space of all images. What I mean? I mean that we have the following simple statement. It can be formulated as a lemma that for arbitrary mu, which is probability distribution of sigma field B, there exists a sequence of discrete probability measures again B such that mu n weakly converge n tends to infinity. So what I'm claiming is that any probability distribution can be weakly approximated by the discrete measures, discrete distributions in our space. So suppose that we have our distribution mu, then we know that x is separable. Yes, x is separable. Then I can find a dense x is separable. Then for arbitrary n, which is greater than 1, I can represent x as a union of force. Okay, so 1, 2, 3. B okay, 1 over m. Maybe here put m. So x is equal to union of some poles. And what I will do, I will consider the following construction. Firstly, let's draw a picture. This will be the first ball. This will be the next one, and I will just remain the part of this ball which is new for us. Yes. So we just add new balls, and in this way we get such a partition of our space X onto the sets with diameter not greater than 2 over M. Formally, it can be easily written as follows. Just define C K M like B U K M 1 over M minus the union of J equal 1 to K minus 1 B U J M 1 over M. Yes, with the agreement when K is equal to 1, this is M. So we get the representation of X as the unions. X is equal to union of this CKM, and moreover, now I will count only non-empty sets. So after this procedure, I check the sequence and put here only non-empty set. If it is necessary, we can re-index this set. After this, so I suppose that this is of CKM is less or equal to whatever. Now let us take the point. Let us take the number. Let us take a capital number M. M in such a way that mu of the union from K equal N, M plus 1 to infinity C K M is less than 1 over 2 M. Then define finally a discrete measure on the space X corresponding to the index M as follows. Just take U K M. This is a point belonging to CKM. Okay, less than M capital, and define P Km as a mu of CK. Of course, it can happen that this is zero. Yeah, this is only non-negative. This is only non-negative. And it can happen that this is zero. And also take some point U0, which belongs to this is like P0M, and then one can consider finally this can measure M, which is equal P0M delta U0 plus sum from K equal 1 to N capital M Pk delta UKM PKM. Okay. Then this
is U0 just any arbitrary point?
Yes. You see, I'm not care about special choice. Okay, you can fix it for any M. The same. I'm not care about this point because its probability tends to zero. Yeah, its weight tends to zero. So finally, it disappears. So we have such points, and now let's go to check. Let's go and check that we have the desired convergence. So what we need to check, we need to check that mu n weakly converge to mu n tends to empty. In order to do this, let us consider the difference of integrals between these distributions. But what I am going to do, I am going because we already have something. So why not to use what we already did? How I want to apply this as follows. Now I will use the following trick, which is very common for the theory of measures on abstract spaces. I will consider the following probabilities. This X, B, and mu. Yes, this is space. This is sigma field, and this is probability measure on this sigma field. Yeah. So let us define this as follows. After this, I will define random elements, which are defined on this probability space with values in X. So let us define random elements. First of all, one random element is for psi of omega will be equal to omega for any omega which belongs to our space X. Okay. So now it is a random element here. And then define psi m of omega. It will be U K M if omega belongs to this C K M. And it will be U0 if this is for K belong to union of K equal M capital M plus 1 to infinity of C K M. Okay, so let us define this random elements in such a way, and it can be easily checked that this is exactly a random elements. In first case, this follows immediately. It follows immediately from this definition. In the second case, it follows from the definition of the sets. These are Borel sets, of course, because they are different. So open ball minus union of open balls and so on. So these are Borel sets. And due to this, these are random elements. And of course, it is easy to see that now mu n is the distribution of psi n, and mu is the distribution of psi. Yeah? So mu m is now the distribution of psi m. And is a distribution of psi. Yeah. And what is remaining? We have to check that we have a convergence probability, and then we will apply our second example. So let us check the probability that rho psi m omega psi omega is greater than epsilon. Of course, we know from the serial convergence probability that here I can put not epsilon, but for example 1 over m. Yes, so let's put here 1 over m or 2m. It's much better. 2m. Then what happens? If omega belongs to union of the k equal 1 and capital M, this C K M, then this rho psi M omega psi omega is less than 2 over M. Let's put here less than 2 over. It follows from the definition of our random elements. We know that the diameter of this set is exactly is less than 2 over m. Then this we know, and we know that in opposite case we have maybe we have big distance, but this is less or equal than 1 over 2 m. So we get the desired property psi m tends in probability to psi, where m tends to infinity, and consequently we get the result. Consequently, mu n tends to u m under m tends to infinity. That's all. By the way, here we have much more strong convergence. One can check that due to our choice, now we have actually convergence with probability 1. And we will see in the future that it is a very interesting remark relatively to big convergence. Another remark what I have to say, that we began this exam saying discrete if we want to be formally rigorous, then we must say that maybe it is a distance in the space of probability measures related to the big convergence, and relatively to this distance, discrete measures are dense. It is exactly true. Such distance can be defined, this so-called Wasserstein distance. It is related to the big convergence, but this is not a subject of our considerations. So we have seen examples of the big convergence. Now let's go further and try to ask the question: how we can detect weak convergence of probability distributions on our abstract space X? Maybe you remember that when we consider R and we have probability distributions on the Borel sigma field in this one-dimensional space, then one can define the distribution functions Fn from U will be equal to the UN from minus infinity U, and in the same way F of U is equal to mu of minus infinity U, and it occurs that meeting conversion U when n tends to infinity, if and only if f of u, fn of u tends to f of u when n tends to infinity at any point of continuity, point u of continuity of f capital. So it was maybe the first criteria of the weak convergence which we obtain when we consider distributions on the one-dimensional Euclid space. So let's think now how this criteria can be generalized to the arbitrary abstract space, just metric, complete, and separate. And to do this, let us think a little bit precisely about this situation. So let me draw a picture with this distribution functions in simple case when mu n and mu are just delta measures as we discussed before. Consider sequence UN which tends to our final point U, but now I will discuss two cases. One is consider the case when UN increase to our limit point u n tends to infinity, and mu n is delta measure concentrated at un, mu is delta measure concentrated at point u. Then let us draw a picture with the distribution functions. This is at point u, and this measure has the following distribution function. It is equal to 0 up to moment u, don't including it, and then it has u. This is a distribution function, and the same kind has a distribution function of measure mu n. It is right, but it is presented by the same step function, which has a step in a different point u. Here, yeah, here is it. And what happens? You see? Then if n of u is equal to 1, because un is less than for any n greater than infinity, and f of u is also equal to 1. Yeah. It's also equal to 1. So what we have here? We have that now limit on the n tends to infinity. F n of u is equal f of u. It's great news. Maybe we don't need this additional sentence at any point of continuity. But unfortunately, this is not true. Let us consider the following situation now, when u decrease to u, yeah, in this way. Then our picture change in such way. Here u n now, and we will have such step function, and it is equal to 0 up to this point, yeah? Up to this point. And in this case, one can see that fn of u equal to 0. So what we have? Of course, we have the now limit and the n tends to infinity. And the n tends to infinity of fnu is not equal to f of u. It's a bad thing. It's a bad thing, but maybe we can try to unite all this knowledge together and try to write mathematically right formula. Yeah, let us do this. And I think that maybe it can be written as follows. Let us write. Instead of the limit, I will write upper limit. When n tends to infinity, n tends to infinity, f n of u, and what I can say, it is equal to 1, but let us write it as follows. F of u. Yes. Now I am formally right. Yes, at least in this simple case. Now let's try to prove this in general case. Let's try to prove this in general case. Let us check. So I want to check such a statement and proceed as usual. We can consider our space, our real line. Here is point u, and now let us define the continuous function. Let us define continuous function f, which will be the following. Suppose that f has the following kind. Here is it. Here is 1. So this is the usual step up to the moment u. Here is u plus epsilon, and the will be a function f epsilon. Then what we know, that the integral with respect to r f epsilon v, excuse me, f epsilon v mu n dv must converge to integral with respect to r f epsilon v mu. And of course, I can write it as follows: limit under n tends to infinity is equal to this one. And you see the picture, and it is evident that the upper limit under n tends to infinity of f n of u is less than this integral, yeah, because fn of u is exactly the weight of this half line, yeah. So it is lesser than, and this holds for any epsilon. But now, if we are approaching u by tending epsilon to 0, then this integral converge to f of u when epsilon tends to 0. Well, actually, this is all. We get the desired property. And maybe it will be not a surprise, if now I will say that the form equality holds that the upper such a limit of f n of u minus, yeah, is greater or equal than f of u minus. This is the usual notation. This is left limit of this function at the point u. Left limit of this function at the point u. We have such equality. And please check this and check that this is enough to have the convergence. This is enough to have the convergence together. So one can now ask why I'm paying a lot of attention to the example, which is definitely non-extendable to the abstract space, because we have no distribution function. So we have to change the conclusion of this example. And let me do this. First, what a set we have here? We have a set of such kind. What is the value of measure on this is u with sign, yeah. So this from the point of view of distance, this is a closed set, and this is open set. It means that now we can at least make a hypothesis that if we have general situation x rho, then if one mu n weakly converge to mu, n tends to infinity, then if B is closed set, then mu upper limit when n tends to infinity, mu n of B is less or equal than mu of B. And if B is open set, then this limit from above lim of mu n B is regular equals mu B. And we will see that this is true. And this is a useful criteria of the convergence in the arbitrary space. But we will do this on the next lecture. Today that's all. Thank you for your attention. Maybe somebody has questions, please. Okay. If there are no questions, then thank you again, and bye for the next week.
Bye, thank you.